All right, hi everyone. So this is FinAP, my implementation of the AI-enriched financial audit pipeline. So this is a MERN-based audit command center for general ledger journal entries. So a journal entry is an accounting transaction, and in double entry bookkeeping, it's debit and credit should balance. So the system identifies risky or unusual entries, explains the detected signals, and lets an auditor search for similar financial activity. So in this demo, the AI layer is intentionally mocked. So rather, my focus was therefore on the engineering around the enrichment, like data ownership, async processing, safe recomputation, migrations, concurrency, and observable audit workflows. So let's start with the code itself. So I'll open the journal entry. So each MongoDB journal document has four explicit boundaries, like the core, here it is, which contains the authoritative ledger fields like posting date, transaction type, debit, credit, amount, description, name, company ID, and etc. And the next is intelligence, which contains risk, anomalies, compliances flag, and these vectors. It is a three-dimension vector which has semantic, financial, and entity spaces. And then model and rules version. After that, we have metadata, which contains auditor comments, workflow status, and audit trail. And at last, we have processing, which contains the intelligence version and durable queue coordination state. And this separation is quite important because the fields have different invalidation rules. So a core accounting change invalidates all intelligence. A rules change invalidates only risk and compliance. An auditor comment invalidates nothing. So the backend is split into class-based routers, controllers, and services, and even repositories. And it is a class-based worker. All repositories own targeted MongoDB operators such as $set, $push, $increment, and $unset. So services own businesses' decision and orchestration. Let's move on to the application. I'll just hit the create journal entry and create a new journal entry. Right, excuse me, let me create demo. Let's name it 001. Name will be ABC Traders, I guess, Private Limited. We'll keep the posting date as today. Posted by auditor for the demo. The amount will be 125K. Same goes for debit and credit will be 0 for now. GL number, let's keep this. And the description will be manual adjustment for raw materials. All right. Okay. So I haven't launched the application yet. My bad. I'll quickly do it. So let me first stop the worker. So it should automatically process it, but the worker isn't running as of now. Only client and the front end is running. Client and the server, sorry. So I'll just quickly rerun the worker as well. And it says it has completed the entry enrichment. Yes, it is now moved to a newer state. So, all right. So this is basically the scenario A, which is real-time ingestion. So the post request validates and stores the journal entry as pending and persists a durable enrichment intent. So the API returns without performing the expensive intelligence calculation in line. So the implementation uses a Mongo DB backend backed job queue. So I chose this for a self-contained assessment deployment. It gives me atomic claims, persistent retries, and no additional broker dependency. So the worker claims the job and runs the required explicit 400 millisecond mocked model relay. So now it is ready. So the dashboard polls active entries and now shows the entry as ready. The risk is high because the amount crosses the review threshold. Debit and credit do not balance, and the description contains the manual adjustment language. So we'll hit inspect. Uh, right. So here's the risk. It is zero point 0.9. The risk is calculated between 0 to 1. We have anomalies, like I explained earlier. These were the reasons. The compliance is also there, and we have the vectors as well. So the diagnostics model exposes the three intelligence requirements. First, the context-aware risk scoring, which returns a value between 0 and 1 and maps it to low, medium, and high severity. The score is factor-based and capped at 1. Secondly, the anomaly detection returns a granular signal objects rather than an only a boolean. So each result identifies its type, affected fields, and explanation, and the confidence. Here we can see the numeric outlier, debit credit balance mismatch, and semantic anomaly. Moving on to the third, the mark engine produces three independent vector, sorry, 8-dimensional vector, because this is 8. So these spaces, the semantic vector model the description, financial vectors encode amount and balance patterns, and the entity vectors represent company, GL, and posting relationships. So they are deterministic and normalized, so the same input gives reproducible results without claiming to use an external model. And the similarity endpoints computes cosine similarity within the selected space, sorts descending and returns the top five ready entries, keeping the search strategy explicit, avoids mixing incompatible meanings into one score. So we'll choose the semantic first, find similarities. So we got the top five. All right, so moving on to the second scenario, scenario B, which is core ledger modification. So right now I'll just change this amount to maybe 6.5, and I save it. It becomes stale, then it gets recomputed. Let's check the log. Here we go. It is successfully recomputed. Yes. So this is basically scenario B. The update path does not assume that every edit needs the same response. A delta service separates core changes from metadata changes. Changing amount is a source data change, so the repository immediately clears. The old risk anomalies, flags, vectors, and model metadata marks the entry stale, increments its intelligence version, and queues a full recomputation. That intelligence version is also a concurrency token. Every worker command carries the version it was created for, and final writes require the entry to still have the version and still be processing. If a newer edit happens while an older job is running, the older output cannot overwrite the newer ledger state, which is a good design in general. So let's just hop to scenario E, which is metadata only update. So I'll click on edit again. I'll change the status to, let's say, closed. I'll click save metadata, and I'll go to author, change it to reviewer, and I'll type something like reviewed during assessment walkthrough. I'll add comment. All right. So the terminal stays quiet. So scenario is deliberately different because the workflow status and comments describe the audit process, not the financial substance of the entry. So these changes use immediate targeted metadata updates and do not increment the intelligence version or create a worker job. So that's why the worker is silent. Uh, anyway, the unchanged worker terminal is visible proof that the metadata updates bypass decomputation. All right, let's move to scenario C, which is model upgrade migration. So I'll go to a fresh terminal. Just for the information, this application is already seeded, so I don't have to seed it once again. So I'll just run migrate commands. So the migration is completed, but we didn't had anything in the queue. So basically, scenario C handles a system-wide model upgrade. So historical entries using the old version become stale, but the loading the entire collection into memory would not scale. So the migration captures an upper bound ID, scans in stable underscore ID in order to using bounded cursor batches, persists checkpoints and enqueues jobs for exact target model and rules version. So this wait, yeah, here this options waits for entries in the bound scope to attain the target version. If a concurrent edit causes a compare and set miss, the run pauses without checkpointing the past that entry and exists are non-zero. It can then be resumed with hyphen hyphen resume hyphen hyphen wait command. So running the command a second time demonstrates idempotency, which is already migrated. So records do not create new jobs. So let's move to scenario D, regulatory rules shift. All right. So scenario D demonstrates selective invalidation. A regulatory or threshold change affects risk and compliance, but the expensive semantic, financial, and entity vectors are still valid. The recalculation service therefore uses a targeted repository update for risk score, severity compliance flags, rules version, and timestamp only. So no vector path is included in the mutation. This is both a correctness and cost decision. Recomputing embeddings when the underlying content has not changed would waste compute and increase latency. So the integration and browser tests are also compare the complete vector object byte for byte before and after this operation. So when I've changed and recalculated the rules, the risks has changed and the compliance has also changed. All right, let's move on to queue reliability and race conditions. So I'll move to journal entry repository on processing job. Yeah. So the S so this MVP also identifies asynchronous design and race handling as primary review topics. So the queue uses an atomic find one and update claim. All right. So concurrent workers cannot claim the same available job. A deterministic deduplication key covers entry ID, job type, intelligence version, model version, and rules version. So jobs include leases, unique lock tokens, attempt counts, exponential retry timing, and terminal failure. Job completion and retry transitions require the current lease identity. If a worker crashes on its final attempt, another worker reclaims and terminalizes that job one at a time and marks only the matching entry version field. So there is also a durable queue intent on the entry. So on a transaction capable Mongo deployment, entry mutation in queue and intent cleanup share a transaction. On standalone Mongo, an uninterrupted enqueue leaves the intent in the entry, and running npm run reconcile jobs repairs it using the same deduplicated enqueue path. And the worker has gracefully shut down handling and waits for an active claim before disconnecting. So these controls give at least once processing the independent and version guarded stale transitions. So I would not describe this as exactly once delivery. So let's move on to the front end constraints and some UX safety. So this MVP explicitly prohibits React hooks and functional primary components. So the UI uses class components. So the and lifecycle methods throughout. The dashboard owns loading, polling, filtering, and model state. Let's go to the audit dashboard. And creator and editor actions disable duplicate submissions, preserve recoverable state failures, and separate core, metadata, and comment commands so the UI mirrors the backend invalidation model. Model ownership prevents a late response for one entry from updating a model that has already switched to another entry, and the polling flow avoids stale refreshes, overwriting newer user action. All right, coming to verification. I'll just run this API port command. So the release gate combines server, unit, and service tests, React component tests, real MongoDB integration tests, the production client build and playwright tests on desktop and mobile, and the browser test executes scenario A through E and all three similarity strategies against an isolated API worker client and MongoDB stack. So let's just go through this. So excuse me. So each suit has different tests, and the test is already present. You can see it on the terminal as well, and it has successfully passed without any errors. So let's talk about some trade-offs, scaling, and uh, then we will close this walkthrough. So for this MVP, I choose a MongoDB backed queue because it keeps local execution simple while still demonstrating atomic claims, leases, retries, deduplication, and recovery. At larger production scale, the worker-facing repository boundary could be replaced with SQS, Kafka, RabbitMQ, or BullMQ without changing the domain services. For much larger similarity datasets, I would move vector search from the application process to MongoDB Atlas vector search or a dedicated vector database. Add tenet scope indexes and paginate or stream operational views. I would also add authentication and role-based admin access, centralized metrics and tracing, alerting for QH and terminal failures, rate limits, and a managed dead letter workflow. And the key design principle across the project is selective recomputation. Core changes recompute all intelligence, rules changes update only rule dependent fields, and the meta changes bypass the worker. Combined with the version guarded writes and bounded migrations that keeps the audit pipeline and correct and efficient under the concurrent change. So thank you for reviewing the implementation.